think this will be a quite fundamental introduction of Gaussian process regression. And in the end, I will talk a bit about a Gaussian process approximation method, that is the Marquee approximation. So yeah, if you are already familiar with Gaussian process, maybe the first half will be a little repetitive.
I think we can get started now, Jian.
Okay. So yeah, thanks for joining, everyone. My name is Jian Cao, and I'm a postdoc at Texas A&M Statistics Department, and I'm also affiliated with TAMIDS, the Data Science Institute, and I'm working with Dr. Matthias Katzfuss. And the tutorial I'm giving today is Gaussian process regression, and a caption of it is it's a flexible nonparametric model that automatically performs uncertainty quantification. So this is an overview of my talk today. In the first part, I will give a high-level overview about where Gaussian processes fit in the big map of various models and which kind of problems can you directly apply Gaussian process. And the second and third topics are a basic introduction of multivariate normal distributions and the extension of Gaussian processes. So Gaussian process is an extension of the traditional multivariate normal distributions. And the fourth part, I will talk about the perimeter estimation for Gaussian processes. And fifth part, after perimeter estimation, what we eventually want to do is probably posterior inference, which is making predictions and uncertainty quantification. And the sixth part, so the first 5 parts covers Gaussian processes, and in the sixth part, I will go through a computational technique for a Gaussian process approximation for computation benefits. So first, where does Gaussian process fit in the big map? So in terms of prediction, we have regression and classification problems. So for regression problems, I broadly think that the response is continuous, and this will be a regression problem. If the response is discrete, for example, if the response is which kind of flower this plant belongs to, then this is a classification problem. So in the left panel, I show a linear regression example that predicts a continuous response. And in the right panel, I show a clustering example that predicts which flower family or which category of flowers does the plant belong to. So Gaussian process is a model for regression, but is a model for regression, although it can also be adapted to for classification problems. But more commonly, it is used for regression problems that predict continuous responses. And the second categorization for models I would like to talk about is parametric and non-parametric models. So for parametric models, the distribution of the data can be characterized by a finite set of parameters. And examples include linear regression models and linear support vector machines, which is a common model in machine learning. Also, the broadly used neural network I believe is also a parametric model, although some people claim that extremely deep and wide neural networks converge to non-parametric models, but they are typically, I believe, parametric models. And non-parametric models typically have infinite number of parameters, and examples include Gaussian process and decision trees. And I believe that a rule of thumb to distinguish the two families is for parametric models, once you feed the model with your training data, and you don't need the training data anymore to make any prediction. And for non-parametric models, after model feeding, to make a prediction, you still need the training data. And that is the rule of thumb in my point of view. And for example, for Gaussian process, after model fitting, when computing the posterior mean and posterior standard deviation, you still need the responses you use for training your model. So is a decision tree. A decision tree has many branches, and at each leaf node, you will average all the responses that belongs to that leaf node, so that the predicted value is dependent on the responses in that leaf node. So yeah, Gaussian process is a non-parametric model, and non-parametric models are usually more flexible and more highly expressive. So here's an example of Gaussian process regression. The observations are denoted by the red dots, and they are generated by the true underlying model of the black dashed line. So if we fit a Gaussian process to these observations, we get this blue solid curve. So we see that Gaussian process is highly flexible, as it can capture the very irregular shape of the observation, and also the true underlying model. And another feature we observe is that at locations where the observation is sparse or non-existent, the confidence interval indicated by the shallow blue area is wider than the area when observations are sufficient. So now let's dive into, so in the previous section, I was basically saying Gaussian process is a model for regression problems, and it is a non-parametric model that is very flexible to capture most smooth shapes. And here, let's dive into more details, starting from the univariate normal distribution and go all the way up to multivariate normal and Gaussian processes. So the univariate normal distribution is characterized by two parameters, the mean parameter mu and the standard deviation parameter sigma. So if you have taken courses on hypothesis testing, I'm sure you are very familiar with this table. It tells you that the p-value essentially, and the p-value is essentially the cumulative probability function of the standard normal distribution. So there's nothing too much to talk about univariate normal distribution. And the multivariate normal distribution is a very intuitive extension. So the mean, compare with this representation, we essentially extend the mean parameter to a vector, and the variance parameter sigma square, we generalize it to a matrix because there's a correlation between the coefficients in this multivariate normal distribution. So this is the density function of the multivariate normal distribution. And yeah, I forgot to mention that mu is a length n vector, and sigma is a n by n covariance matrix that is positive definite. So here, notice that to compute this density function, we need to compute the determinant of the covariance matrix and also the inverse of the covariance matrix, which are all the three operations with respect to n. We will go through computation details later as well. And here I show a simple example of n equals to 2, where we can still visualize this density function. So basically, if we rotate this this quadratic shape along this vertical line, mu x equals to mu, then we can get something similar to this. It's feels like a cone. So it's a very intuitive extension of the univariate case. And the reason for the popularity of Gaussian processes or the popularity of multivariate normal distribution is because the nice properties of the multivariate normal distribution, notably the marginal, notably being closed under marginalization and being closed under conditioning, which means that if we have a joint multivariate normal distribution, and if we consider a subcomponent of this joint random vector, we still get multivariate normal distribution. And for marginalization, if we consider, for example, x2 only, then x2 is a multivariate normal distribution with the mean parameter and the covariance parameter directly taken from the original joint distribution. So if we take these directly from the lower half of the mean vector and the covariance matrix, we get the marginal distribution of x2. And for conditioning, we have a slightly more complicated formula. But essentially, we can view it as this is the impact of x1 on the mean of x2, and this is the impact of x1 on the covariance of x2. So essentially, if we fix x1, the variance of x2 also reduces. So yeah, this slide is basically saying the multivariate normal distribution has very nice properties that include being closed and the marginalization and conditioning. And the formula is also not too complicated. And here, to better understand the conditional normal distribution, I provide a visualization. So in this transparent shape, this transparent shape is essentially this density function for bivariate normal distribution. And if we fix x1 equals to 1, and we consider the conditional distribution of X2, then basically what we are talking about is the red line or the red curve here. So it is the intercept between the vertical surface of x1 equals to 1 and the original bivariate density function. And if we extract this red curve, we get something on the right-hand side. Yeah, this is just a visualization of the conditional normal distribution. So now that we have covered the univariate normal distribution and multivariate normal distribution, let's go a step further to a generalization of multivariate normal distribution, that is Gaussian processes. So a Gaussian process is also defined by the mean structure and the covariance structure. But in multivariate normal, we have a n-dimensional vector and the n by n matrix. Whereas here, we have a mean function, mu, and a covariance kernel function, k. So when we are talking about a Gaussian process, we usually say where the Gaussian process is defined. So here we generally say that this Gaussian process is defined in a d-dimensional domain X that is a subset of Rd. And for any arbitrary number of locations within this domain X, denoted by S1 until Sn, the corresponding observations are denoted by X1 until Xn. And X1 and Xn, X1 until Xn, these n random variables will have a joint multivariate normal distribution, since they are realizations of this Gaussian process at n locations. So the bolded X, which is X1 until Xn, has a n-dimensional joint n-dimensional normal distribution parameterized by the mean parameter. So the mean parameter is essentially the mean function applied to each of the n locations. And the covariance matrix is the covariance kernel applied to each pair of the locations. So for the covariance kernel function k, it has to be a positive definite function, which means, of course, k has to be, well, the arguments of k has to be mutable. Well, let's say ks1, ks2 have to be the same as ks2 and s1. And also, well, there's it's difficult to describe which kind of functions are positive definite, but there are existing, there are families of functions that are already identified to produce positive definite covariance matrices. For example, in spatial statistics, k is usually chosen to be a maternal covariance kernel that is parameterized by 3 parameters. And in machine learning, k is frequently the squared exponential kernel. And in physics, k is usually of some other functional form that I'm not too familiar with. So notice that not every distribution can be generalized into a process. As you can see here, process is stronger in some sense than a distribution, since you can choose any arbitrary number of locations within the domain and get a distribution but not any distribution can be generalized into a process. For example, a skew normal distribution is typically not generalizable into a process. And Gaussian processes, here I provide two examples to better understand Gaussian processes, as well as where Gaussian processes can be applied to. So in the left figure, I show the temperature. Remember, it is temperature of the region near Saudi Arabia. Yeah, so we can view the temperature as a random process defined over the region, over the geological, over the region on the surface of Earth. And so each S here corresponds to the longitude and latitude, and each X here will correspond to the surface temperature. Sorry, it's written here, yeah, temperature, and each S is a location on the Earth's surface. And another example is the MRI images of human brain. So for MRI images, there are several layers, and what we are interested in is usually the correlation between the activation levels of different regions. So for this application, we can define SI to be different regions in the human brain, and XI to be the activation level of that region. So yeah, hopefully these two examples can help you understand better what are processes in general, or what are stochastic processes in general, and Gaussian processes can be, in principle, used to model these this type of data. Although the real data may not is probably not from a Gaussian process exactly, but we can still use Gaussian process to model this data. And yeah, feel free to interrupt me if you have any question, since I've been keep talking. So here I summarize the typical procedure for fitting our data with a Gaussian process. So the first step is pretty much needed for every single model fitting, not limited to Gaussian processes, that is data processing. But for Gaussian processes, usually you will need continuous responses and continuous features or coordinates or locations, whatever you call it. So you'll probably want to make them continuous and try to standardize them into the same scale. And the second step is to choose a proper mean and covariance structure that parameterizes your Gaussian process. So for example, you can choose a linear mean. So here, if you choose mu to be a linear function of Si and K to be for example, a Matern covariance function, yeah, that can be a typical easy choice. And the third step is to estimate the parameters of your Gaussian process. So you have some parameters in your mean structure and some parameters in your covariance structure. And usually for statistic models, the typical way to estimate the parameters is to maximize the likelihood or the log likelihood. And well, the fourth is naturally making the fourth step is also our final goal to make predictions. And also we can also make uncertainty quantification using Gaussian process. So now that we have talked about Gaussian processes, and the next topic the next topic is a parameter estimation. And for statistic models, the way we estimate parameters is usually the maximum likelihood estimation, as mentioned just now. So use theta to denote the parameters for the mean structure and the covariance structure. The maximum likelihood estimation optimizes or maximizes the log density function. And assume that the data is generated from our assumed model. In other words, assume that the model we choose, which means Gaussian process, the mean structure, and the covariance structure are correct. Then the maximum likelihood estimation will lead to asymptotically zero bias, and also asymptotically the smallest possible estimation variance among the unbiased estimators. So in other words, if our model characterization is correct, then the maximum likelihood estimation can be shown in principle to produce the best estimates.
Hey,
So
Jian, there is a question. There is a question in the chat room. Do you want to answer it?
Okay. Oh yeah. Sorry, I just see it. Yeah. So. Yeah, that's a very good question. So for a process, you can think of it as being defined over all the space. For example, if the space is Earth's surface, then you can, if your response is temperature and the space is the whole Earth's surface, then you can view the temperature as a process over the surface. Whereas a distribution is if you have 10,000 sensors on the Earth's surface that measures the temperature, then the measurements from these 10,000 sensors are 10,000 random variables, and they have a joint distribution. And this joint distribution, well, that's a distribution. If you consider the sensors, that's a distribution. If you consider the temperature on the whole surface, there's of course, uncountable number of locations, then it's a process. Yeah, I hope this will help clear your question. So yeah, so for Gaussian process, the typical way for estimating the parameters is maximum likelihood estimation. Unlike in machine learning methods, where we usually minimize the RMSE, the root mean squared error, but for statistic models or specifically Gaussian processes, we usually do MLE instead of minimizing the RMSE. So here's an example showing the importance of parameter estimation, or the importance of optimizing the model parameters. So here the data set is a height and weight data set. On the x-axis, we show the height, and y-axis shows the weight. For each dot here, we have one observation, and so basically, I'm showing something that will be later discussed as well. That is posterior inference. But here, I will just show what is the meaning of the components in the figure. So the solid blue line is the mean estimates. The solid blue line is the mean estimate based on these observations. And this orange band is the confidence interval, also computed based on these observations. So if we compute this confidence interval and also the mean estimates using some random initial model parameters, some random initial theta that decides the mean structure and the covariance structure, then the posterior inference essentially the posterior inference eventually gives us some unreasonable shape. For example, here we are at this deep, we are getting some very unreasonable value. Whereas if we do the same thing, which is estimating the posterior mean and posterior standard deviation at each height value, then we get a much more reasonable shape. Here is much more reasonable than the previous part here. So using a more properly chosen mean structure and covariance structure really helps with the posterior inference. And also here the shape and the confidence interval is a little wider than the other locations, than the other height values, because there's very sparse observation in this region. Yeah. So the previous data is weight and height. So actually the data displays a quite strong linear relationship. And here I simulated 20 data points from a sine function. And if we use some random initial parameter values and compute the posterior mean and posterior standard deviation, we get a pretty wide confidence interval. So the prediction will be not very accurate. In contrast, if we optimize the parameters first with MLE, and with the optimized parameters, we construct the posterior mean curve and also the posterior confidence interval, we got a much narrower confidence interval. So all these two examples is saying the importance of finding a good parameter value usually using maximum likelihood estimation. So now that we know the perimeter estimation for Gaussian processes is usually done by maximum likelihood estimation, MLE. The next step after perimeter estimation would be posterior prediction. For posterior prediction, essentially, we are computing the expectation at some unknown location and also the standard deviation at some unknown location. So the rationale behind the posterior prediction of Gaussian process is the conditional distribution formula that has been shown before. So recall that if x1 and x2 have a joint multivariate normal distribution, then given x1, x2 has a distribution in this form. And when making posterior prediction, we actually consider each unknown location separately instead of considering them jointly. So here, the dimension of mu2, sigma 2 are both 1. So mu2 is a scalar. Mu2 and sigma 2 are both scalars. So that is typically the case when you are doing a posterior inference or posterior prediction. And yeah, and that is, so this formula is also how we get these confidence intervals for each height level and each x value in this figure. And this figure shows the importance of your training sample size on the quality of posterior prediction. So here, both figures compute the posterior mean and posterior standard deviation using the same parameter values, but in the left figure, we compute the posterior mean and standard deviation using only 20 samples, using only 20 training samples. Whereas in the right figure, we have 200 training samples, all of which are used in computing the posterior mean and standard deviation. So we see that when using 200 training samples, the confidence interval is much narrower, and it totally agrees with the shape of the sine function. Sorry. So the posterior inference or posterior prediction is dependent on both your parameter estimates, aka the values of data, and also the number of training data or training observations you used. So this is also corresponding to nonparametric, to the feature of nonparametric model I introduced at the beginning of this tutorial. Actually, no, overfit is a feature. Overfitting is something that happens when your sample size is too small. So when you have, when the number of your parameters is larger or is close to your sample size, and that's when overfitting happens. So for example, if you have 10,000 training samples, but 10,000 training samples, but also 1,000 parameters in your model, then it could be the case that you overfit the model. And in that case, your in-sample training error will be much smaller than your out-of-sample training error. And yeah, in that case, overfitting happens. But as you can see here, the Gaussian process usually have very few parameters. In our case, there are 4 parameters in total, including the mean structure and the covariance structure. And with only 4 parameters, it's usually not the case for to have overfitting. And yeah, so the quality of the posterior inference depends both on your parameter estimates, the values of theta, and also the number of training samples you use to make prediction. And yeah. So now that we have went through the whole process of using Gaussian processes to model your data and make predictions, we will now talk about some computation techniques that will make the Gaussian process more scalable to the data set size. As mentioned before, in MLE, the maximum likelihood estimation, the computation of the objective function, I'll just find that slide. Yeah, the computation of this objective function, which is the density function of the multivariate normal distribution, is cubic in n. So this is not very scalable, especially when n is greater than 5,000 or 10,000. This becomes more computationally infeasible. And for this reason, there are numerous methods that are proposed to reduce the complexity of computing the objective function. And today, I'm only talking about one category of GP approximations. That is the conditional independent approximation. So I'm only talking about this category of GP approximation, the conditional independent approximation. And as the name suggests, it assumes independence between the coefficients of x given some condition. So here, an intuitive expression is as follows. So fx is the joint distribution, and given some condition c, the coefficients in x becomes independent. So essentially, we break down the n-dimensional joint distribution into the multiplication of n one-dimensional distributions. And this intuitive expression here this technique is called fully independent approximation. As you can see, each coefficient is assumed to be independent from all the others given the condition C. And a slight extension is the PIC, which is partially independent approximation. So for PIC, we don't assume x1 and x2 to be of length 1, but rather each x is a group or is a subset of the original x here. So each here in the PIC formulation, each xi is a group of coefficients, or is also a vector, so that these groups of coefficients are assumed independent However, we also assume dependence within each group. So PIC, as you can see here, is a generalization of FIC. And if the length of x1 until xn tilde all equals to 1, then PIC boils down to FIC. So both FIC and PIC are commonly used in machine learning to achieve high computation efficiency. However, I will show that both methods are not cannot provide as close approximation as the conditional independence approximation we want to promote today, that is the Marquee approximation. So the Marquee approximation is a generalization of the FIC as well. So for FIC, we assume all the coefficients are independent given some common condition C, whereas the Marquee approximation assumes they are independent given different conditions C. So instead of using a common condition, the Marquee uses a different condition for each coefficient in X. To better understand the Marquee approximation, let's start from the conditional expression of a joint distribution Fx. So here Fx is some arbitrary n-dimensional distribution, not necessarily a n-dimensional normal distribution. It can be any distribution. And the conditional probability formula says this n-dimensional distribution can be decomposed into the multiplication of n conditional distributions. So we write the first x1 in the unconditional form, and x2 can conditional on x1 only, and x3 conditional on both x1 and x2, so on and so forth. And xn will need to condition on x1 until xn minus 1. So this conditional representation is universal. And what we can do, and what Marquee approximation suggests us to do, is to truncate these conditioning sets. So for example, for xn, we don't condition on all of the previous axes, but we condition on only a subset of these axes. Specifically, we want to conditional on a subset of size m, where m is a perimeter that is much smaller than n. For example, if n is 10,000, we can choose m equals to 30. So each x conditions only on 30 previous axes. And we essentially approximate this n-dimensional normal distribution, or this n-dimensional distribution with n univariate conditional distribution, each with a conditioning set size of m. So if this is the origin or interpretation of the Marquee approximation. And to see how much better the Marquee approximation performs over the commonly used FIC and PIC. So here, this figure measures the distance towards the true distribution, the true underlying multivariate normal distribution. The distance is measured by the KL divergence. So here we see the pink curve, which is the second lowest here, is the Marquee approximation. And the top three curves are FIC, FITC, and PIC. So FITC is a slight modification of FIC, and its performance is usually in between FIC and PIC. But here, actually, FITC performs the worst. And scaled Marquee approximation is also a slight extension of the Marquee approximation, which I will talk about later as well. So yeah, so the Marquee approximations has a much better performance because it uses different conditioning sets for different axes instead of assuming the same conditioning sets for all the axes. And this part makes the approximation much more accurate than FIC or PIC. Here's a typo, sorry. And so here the winner is actually the scaled Marquee approximation. And what is the scaled Marquee approximation is introduced here. So for the scaled Marquee approximation, essentially assigning different relevances to different dimensions of the domain. For example, if we are measuring the temperature on the Earth's surface, I can assign different weights to longitude and latitude. So if we assign different weights and consider the weights in the Marquee approximation, then basically we get the scaled Marquee approximation. And in general, there can be more than 2 dimensions in the input domain, and the more varying the significances of the dimensions, the larger the difference is between the scaled Marquee approximation and the Marquee approximation. So yeah, I won't go through the details here, but yeah, that's the general idea of the scaled Marquee approximation. And here's an example. For the Marquee approximation, we choose the conditioning sets. Remember the conditioning sets CI, which is the conditioning sets here. We choose the conditioning sets to be the M nearest neighbors of the I's observation. So this is a demonstration. This is a demonstration of the difference between scaled Marquee and Marquee. So for the location 28, if we consider each input dimension, or if we consider each dimension of the input domain to be the same, then the nearest neighbors of 28 would be 9, 23, 24, and 11. However, if we let the data decide the weight or the relevance of each input dimension, for example, longitude and latitude, we let data decide the weights, and then we compute a weighted Euclidean distance. Then the nearest neighbors previously computed are 9, 23, 24, and 11. They shouldn't be the nearest neighbors in this scale domain. And 26 and 27 should be chosen instead. And this is essentially the reason why scaled Marquee approximation performs better than Marquee approximation. So the procedure for constructing the Marquee approximation is so for the Marquee approximation, ultimately we want the conditioning sets to be decided. So once you have the conditioning sets, you can just compute n univariate conditional normal distributions. So the first part is ordering the locations, for which we use the max-min ordering that maximizes the minimum distance towards the previously ordered responses. So in other words, you want to choose the locations to be as distributed in your domain as possible. And that is the typical way used for ordering the locations in the Marquee approximation. And the second step is to construct a, okay. So yeah, I think what we want to say is FIC instead of FIA. And for FIC is as I just introduced. So for FIC, you assume independence given the same condition C, which is FIC is essentially given by this equation, and low rank approximation yeah, there are different low rank approximations. One way you can use a low rank matrix to approximate certain blocks of your covariance matrix. And that is essentially based on the fast decrease of singular values of covariance matrix blocks. So so essentially this large matrix block can be closely approximated by the multiplication of two thin matrices. And for a GP LVM, yeah, at this point, I cannot come up with the idea of GP LVM, and you can send me an email, and I can address this question, the GP LVM part, later. Yeah, so the procedure for constructing a Marquee approximation is first ordering, and then finding the conditioning sets, and then finding the conditioning sets, and then just as normal GP estimation, we optimize our objective function and try to find the parameters for the mean structure and the covariance structure. But instead of optimizing the exact GP log likelihood, which is order 3 complexity, we optimize this Marquee approximation of the log likelihood, which is this part. Which is this equation. Or if we take the log, then we have a sum. And essentially, we compute n univariate conditional distributions, and the complexity becomes linear with n, and actually cubic with m, where m is the size of each CI. Yeah, that's the procedure. And for a posterior prediction, we can also apply the idea of Marquee approximation. Specifically, for each unknown location denoted by S star, we can find the M nearest neighbors of this unknown location. And we compute the posterior mean and posterior standard deviation only based on these M nearest neighbors of S star instead of, so if we compute only based on these M nearest neighbors, the complexity for computing the posterior mean and standard deviation becomes M cubic, instead of n cubic. And so here's a summary of the advantages of using the Marquee approximation. So the first one is the purpose of its design, which is to reduce the complexity from n cubed to linear with n. And the second one, as you can see, in its representation, the objective function of the Marquee approximation can be computed in parallel. So each univariate conditional distribution can be computed independently from the others. So the linear complexity with respect to n can be parallel, can be even further paralleled. And the third part is more analytical. So the Marquee approximation is equivalent to an approximation to the inverse Cholesky factor, to the Cholesky factor of the inverse covariance matrix. So the Marquee approximation is equivalent to a sparse approximation of the inverse Cholesky factor. And the false advantage is that the Marquee approximation provides much higher accuracy using the same conditioning set size M compared with other conditional independence approximations that include FIC and PIC. So this is a summary. Gaussian processes are nonparametric and can be directly applied to regression problems. And Gaussian processes are highly expressive. As long as your data is continuous, Gaussian processes can usually capture the features quite nicely. And the Marquee Gaussian process approximation is highly accurate. And in fact, we think the Marquee is the most accurate among the category of conditional independence approximations. And it also has a linear complexity and very good parallel features. And scaled Marquee approximation, so here should be a Marquee left. Scaled Marquee GP approximation makes the accuracy a step further, improves the accuracy a step further, especially when the significances of different dimensions of the input domain are very different. So here are the two references, and also have a Google Colab notebook, which I will share now. So I also share the link of this notebook here. So this notebook may give you some hands-on experience on Gaussian processes or Gaussian process regression using Python. So in the first module, I imported a lot of libraries, but some of them are performing the same task as other functions. For example, multivariate normal, you can either import from SciPy or PyTorch. And also there are other implementations as well. And yeah, probably you also need to install the FIRES library. The FIRES library is a library to find the nearest neighbors of a given location, and it is used for constructing the conditioning set of each observation. So here is a simple demonstration of the Okay, yeah, finding nearest neighbor. Okay, I'll share my whole screen then. So well, let's use this temperature example. Let's use this temperature data, or let's use this temperature example. Suppose we have several sensors on this map, and well, I think I went too far, but I cannot use all the notations I defined later. So finding the nearest neighbors is essentially finding CI. So here we have C1, C2 until Cn. So we want to make this CI as the M nearest neighbors of Xi. So for example, for Xn, the conditioning set should be a subset of X1 until Xn minus 1. And how can we choose a subset? So the way we choose the subset is that we choose the nearest neighbors of S1. And the nearest neighbors of Xn is, so Xn has a location that is defined by Sn. So Xi has a location that is Si. And Si will have nearest neighbors we call Nn. That the nearest neighbors Nn, and we take only the first M nearest neighbors, and we call this the indices of these nearest neighbors to be Ci. And Ci is then used as the conditioning set, which is here. Let's say here. So I hope this will help explain your question. So more specifically, Si can be thought of as a location on the Earth's surface, and Xi is the temperature. And for Xi, if we want to find the conditioning set, we find the nearest neighbors of the location of Si, and we define the indices of the nearest neighbors to be Ci. Yeah, exactly. Points with the shortest distance from Xi. Yeah, for the Marquee approximation. Yeah, X don't have to be on a uniform grid. X can be randomly distributed, even if there are some locations that are very close or even overlap each other. You can still add a negative effect to avoid singularity. And as for the second part of your question, yeah, I did have some experience with larger data sets. For straightforward application of the Marquee approximation, you can easily go to 50 to 100,000 observations. So n equals to 50,000 or 100,000. And if you make some more, if you make some, well, also use the technique of mini batch subsampling. So instead of training the perimeters with all the observations, I use mini batch subsampling. And with the mini batch subsampling, in our most recent work, we reached a GP regression using 1 million observations. But of course, in each training, the I did have some experience with larger data sets. Okay. So this is some simple demonstration of the univariate normal density function. And here is a demonstration of the bivariate normal density function shown here. And so the bivariate normal distribution has a mean structure of 0 and covariance structure of such a matrix. So here, sorry, let me run these codes so that the later part of the code can also be working. So this is a bivariate normal density demo. And this is the univariate conditional demo. So if we fix x1 to be 1, what is the conditional distribution or the conditional density of x2? So here it gives the red curve gives the conditional density. And we can also compute the red curve using the analytical formula of the conditional normal distribution. And we can reach this curve. Yeah, yes, thank you for your question, Minggang. Actually, I think if you're considering conditional independence approximations, the Vakia is better than FIC almost all the time. I mean, yeah, I cannot think of a situation where Vakia performs worse than FIC. The idea of Marquee approximation is the screening effect. So if you have observation here and you have observations, so this is your eyes, you have several observations. And the Marquee approximation's idea is once you have conditioned on the nearest locations, the further locations will not have much impact on the conditional distribution anymore. So in other words, even if you add this location, if you add it to the conditional set, right now we're conditioning on three closer locations, these three, and even if you add this one to the conditioning set, it wouldn't make much difference to the conditional distribution anymore. And this is called the screening effect. And for FIC, you have several locations, and the conditioning set for all these locations are the same. So for all these locations, the other 6 locations, you are conditioning on the same set of locations. Here, for example, these 3 locations, this is the common conditioning set, and this is FIC. And in comparison, for Vakia, you are changing this conditioning set for each location so that they are closer to the current location, to the eyes location. And that is why Vakia is so much more accurate than the FIC approximation. And yeah. So here's well, here's the data set of weight and height. Yeah, I'm not sure if I should go through all these examples that whose results have been shown in my slides before. But yeah, this is loading the weight and height data set. And here I choose a subset of 5,000 observations. And if we consider only height, which is our Y, the responses, the marginal distribution of the responses is looks like this. And so this is some hypothesis testing example. So if you are asked to construct a confidence interval for the mean of population height, then yeah, you have a histogram, and you want to fit a normal distribution, in this case, a univariate normal distribution to this histogram, and see which normal distribution best describes the data. And obviously the red one here is the most appropriate one here. And here we not only consider the height, which is our response, but also the weight. So here the weight is considered the feature or the so-called location also. So we have a Gaussian process defined over the one-dimensional domain of weights. And we can use a constant mean. We can use a Gaussian process with a constant mean and exponential covariance function. Sorry, here should be a negative sign here. Use an exponential covariance function. Then yeah, we can fit a Gaussian process to this weight and height data set. Here's some parameter initialization. Notice that most optimizers in Python, they don't support, well, in my impression, they don't support parameter value constraints. So here I use the log transformation to transform these parameters so that their range is transformed to the whole real line. And this is a function for computing the negative log likelihood, which is also our objective function. So yeah, in the slides, I mentioned that we try to maximize the likelihood, which is MLE. And here we are minimizing the negative log likelihood, which is equivalent. And here we define an optimizer implemented by PyTorch. And these are just standard routine, which can be easily found from PyTorch tutorials. And here, did I run this one? Okay. And here we can run the optimization. And basically, we can run 500 iterations. And at each, so it's also worth mentioning that PyTorch automatically computes the gradient of your objective function, which makes the optimization much faster. In comparison, if you are familiar with R and you run optimization using R optim package, you need to either supply the gradient function yourself or choose some heuristic optimization algorithm that doesn't take advantage of the first order information or the gradient information. And for those algorithms, the optimization is usually slower. So yeah, I think this auto-diff functionality from PyTorch, and there's also other modules in Python that implement auto-diff. This is very helpful for optimization. So yeah, here the optimal, yeah, we're optimizing these Gaussian process parameters. Meanwhile, let's move on. So Yeah, that's a great question. Yes, so I would say the main reason to use Gaussian process is well, there are two main reasons. The first one is data efficiency. So for neural network, you will have so much more parameters, hundreds, thousands, or even more. And for training a neural network, you need a very large sample. And for Gaussian process, the model is usually quite parsimonic, meaning it has very few parameters. And so even if you don't have a very large training sample, you can still feed the model quite well if your data displays some smooth feature. And the second main reason is Gaussian process can, if you feed a Gaussian process, it can provide you error estimate or standard deviation estimate. So for example, if you predict the price of something, and with a neural network, you may not get information on how accuracy your prediction is. Whereas if you're using GP, then you have a uncertainty estimate or uncertainty quantification. And the second reason, or the second part, uncertainty quantification, is also the driving force for the hot topic of Bayesian optimization. So yeah, these are the two main reasons why you can consider GP. So this part is the posterior inference. Thank you as well. I think for the sake of time, I will not run all the remaining codes in this hands-on tutorial, but yeah, you have the link, and I will briefly describe what's remaining in this tutorial. So here's a plot of the posterior prediction using initial random GP parameters. So this is not a good GP, but still we perform posterior inference, and we got this weird shape here. And here we perform posterior inference with the GP parameters after optimization. So we get a much better confidence interval and more reasonable shape. And here's the implementation of the Marquee approximation. So this class basically computes the Marquee log likelihood in the forward propagation part. So this class is based on the N module class in PyTorch, so that the auto-diff functionality can be directly applied. And yeah, this is an implementation of the Marquee log likelihood. And here, as you can see, it's computing each of the N univariate conditional density function. So this for loop can be actually fully paralleled. Each computation within this for loop is of order m to the power of 3 complexity. And here's an example of performing GP estimation of GP parameter estimation using the Marquee log likelihood. So here's defining the GP, the true GP, and here we define the Marquee approximation. And yeah, I think I will stop here. And is there any further questions? Hi, Jian.
Yes.
Oh, yeah, I think, yeah, I think I will stop here. And is there something you would like to share with others, or I should know?
Sure. I think you already shared the link to the Google Collaboratory, the notebook, GP notebook. And someone also asked you about your email address. And for the slides, I think we'll share at some point. We'll need to create a web page for all the webinars and get your slides shared as well.
Yeah, sounds good.
Yeah. Okay, if there are no more questions, we'll end this webinar, and there will be some follow-up webinars in the near future. We are still waiting for the schedule for the summer to figure out what we want to do for the summer. But if you stay tuned on the announcement of TAMIDS mailing list, you should be able to get the latest updates from our side. And thank you all for attending the webinar today. And hopefully, we'll see many of you in the future, virtually, or maybe sometime in person in the future. Okay, thank you so much.
Thank you very much.
Thank you.
Thank you.
Bye-bye.
Thank you for attending.
Thank you. Bye.